All right. Good afternoon. Just going back to what we have with functions and inverses, and we looked at from last time. Okay, we had worked with exponential functions as well as logarithms, and just kind of doing a little bit of recap. Okay, and we have again we have an exponential function y is equal to f of x is equal to a to the x. And again, we have for the conditions, okay, we have that the exponential base a is positive with the exception of 1. And for the power of x, okay, x could be positive, it could be negative, so you just have like all real values x. But again, whatever we have for y, okay, for the exponential function, y has to be positive. And right now for the domain of the exponential function, okay, this will be your set of values x, and that's going to be the set of all real numbers, okay. And for what we have in the case of the range of f of x, yeah, kind of improvised, got a little bit into a little bit of a rush. Okay, for the range of f of x, that's going to be your set of values y. So you have positive values throughout. Okay, so going from 0 to infinity. And for the inverse, okay, so the domain, okay, you have positive values in x. Okay, so again, you're looking at interchanging x and y. Okay, and so we have in terms of the spreads. Okay, so for the original function, what we have in x, we're going to have in y for the inverse, and vice versa. Okay, so again, going back to our exponential function, if I interchange, again, I have x is equal to a to the y. And again, to take care of the exponential base a, once again, I'm going to take logarithms in the matching base, in this case, which is going to be a. So I have the base a logarithm of x is equal to y, and then switching the order, we have y is equal to the base a logarithm of x, and again this y will be making reference to the inverse of f of x, and again that is going to be the base a logarithm of x. Okay, and just to kind of give you a bit of an example, okay, of what we have with exponential functions, okay, and we can start out. Let's say if you're looking at the determining the inverses, the domains, and the ranges throughout, and we can say that we have, for starters, and it's going to get just a little bit analytical, but not so much for what's going to be on the test, but just for what is going to appear in ALEKS. Now, let's say if you have your exponential base to be at 3. Okay, and just some items here. Okay, so we have for y is equal to f of x is equal to 3 to the x. Okay, now for the domain of f of x, for the domain of f of x, okay, this is the exponent. So x could be 0, it could be a positive, and again, it could be a negative. So you have going between negative and positive infinity. And in terms of what we have for y, what we have in the case of y, okay, so again, the minimum value that we're going to have for y is going to be the least possible positive value. So y is going to stay as greater than 0. Again, so we have for the range of f of x. Okay, so this will be positive values in y. Okay. And just looking at taking the inverse. Again, so we have that y is equal to 3 raised to the x. And in looking for the inverse. Okay, so as I look at interchanging x and y, okay, so here we'll have x is equal to 3 raised to the y. And I want to get this equation where y is going to be freed up from the power position. Okay, so I'm going to take care of the 3 upon taking both sides and applying base 3 logarithms. Okay, so here I'm going to have the base 3 logarithm of x is equal to the base 3 logarithm of 3 raised to the y. Okay, so we have, in this one, we have the base 3 logarithm of x is going to be equal to y. And if I switch the order, okay, so I have y is equal to the base 3 logarithm of x. And so we have for the inverse of 3 raised to the x. So this will come out to the base 3 logarithm of x. And now for its domain and range. Okay, so again we have for the domain of the inverse. Again, what we had in y for the original function, we're going to have an x for the inverse. Okay, so you're looking at positive values in x. Again, just swapping again, okay, for the range of the inverse. What that will have in y will be what we had in x for the exponential function. Okay, so that is going to be the set of our real values. Okay, so y equals 3 to the x and y is equal to the base 3 logarithm of x. You're going to have an inverse relation in the sense of having interchanging x and y values. And again, the graphs will run symmetrically with respect to the line y is equal to x. And I was able to get a graph of these items. And let's say that for what we have in the case of y is equal to 3 to the x, as well as the base 3 logarithm of x. Okay, so again we have for the graph, okay, so I have for y is equal to 3 to the x, I have this curve in red, and whenever x is 0, yeah, y is going to be 3 to the first, and when x is 1, y is 3 to the first, which is going to be 3. And say if x is 2, y is going to be 3 squared, and 3 squared is going to be 9. So we have these 3 ordered pairs among the infinitely many points that will make up this graph. And for the base 3 logarithm of x, again, you're going to have to consist of the interchanging x and y values from the exponential function. Okay, so you have 1, 0, 3, 1, and 9, 2. So this curve in green, again, is going to be in reference to the base 3 logarithm of x. And again, we have both of these graphs run symmetrically with respect to the line y is equal to x. All right, so this is just a bit of a dynamic, okay, that is carried out for what we have here. And without changing things up too much, and keeping a lot of the elements the same with just ever the slightest modification. Okay, so this is for 3 to the x. Well, let's say if I have a bit of a vertical shift. And let's say that in the case of the makeup, and just do a little bit of a modification. Okay, let's say if I have a vertical shift, and I had that y is equal to f of x is equal to 3 to the x. And we have followed by the subtraction of 1. Okay, now the least that 3 to the x can be is going to be like an infinitesimal that is greater than 0. And so for what we are going to have here is that for what is going to define y in this particular case. So if you think of like the smallest possible positive value minus 1, the difference is going to be just greater than 0 minus 1. So in this particular case, right, you're still going to have that, instead of y greater than 0, you have y is going to be greater than 0 minus 1. So you have the range is going to be that y is greater than negative 1. And we have for the interval notation, okay, so you're going to have parentheses this time around negative 1 and infinity. And so just looking at what we have now, so you have y is equal to 3 to the x minus 1. And then crossing over to interchanging x and y. Okay, so you have x is equal to 3 to the y minus 1. So again, we still have the exponential base at 3. And we will eventually apply the base 3 logarithms on both sides. But I'm going to have the y term, again, situated by itself. So I'm going to move this one by adding to both sides. Okay, so I'm going to have the x plus 1 is equal to 3 raised to the y. Okay, so I now have, instead of x, I now have x plus 1. And I have is equal to 3 to the y. And again, I'm going to take care of the 3 upon applying base 3 logarithms on both sides. So we had the base 3 logarithm of all of x plus 1 is equal to the base 3 logarithm of 3 raised to the y. And so just looking at what we have now. Okay, so we have the base 3 logarithm of the quantity of x plus 1 is equal to y. And again, just reversing the order. So we have that y is equal to the base 3 logarithm of the quantity of x plus 1. So we have for the inverse, again, the inverse of f of x, this is going to be the base 3 logarithm of the quantity of x plus 1. And for the domain and the range, okay, so for the exponential function, okay, we had, again, the range, you have values of y greater than negative 1. And that negative 1 created from the subtraction of 1. If I had no addition or subtraction of a constant, I still be looking at y is greater than 0. But because of the minus 1, we have this instead. And in the case of the domain, the inverse, okay, so we have between negative 1 and infinity. And for the range of the inverse, okay, that is going to be the set of all real numbers. and just providing, again, a bit of a visual. Okay, now before we had the graph of y is equal to 3 to the x, and to see, okay, how things are going to change with a downward shift of 1 unit. Okay, we have y is equal to 3 to the x minus 1. Okay, so I have with y is equal to 3 to the x minus 1. Okay, so I have like 3 to the 0 is 1. 1 minus 1 is 0. So I have the ordered pair 0, 0. So I have the origin. And if I have like 3 to the first, 3 to the first is 3. 3 minus 1 is 2. So I have the ordered pair 1, 2. And if I have x situated at 2, well, y is going to be 3 squared, which is 9, minus 1, and 9 minus 1 is 8. So I have 2, 8. And so we have with the inverse function, what we have is the base 3 logarithm of all of x plus 1. So again, we're going to have the ordered pairs in reverse. And if you notice, okay, these curves, they meet each other at the origin, and they also come into contact with the line y is equal to x. So the downward shift here with the exponential, it kind of creates in a way an upward shift with the inverse, okay, where they come into contact. Where if you notice before, without the minus 1 attached to 3 to the x, notice you have these curves are apart and are a little bit remote from y is equal to x. Okay, so in this case, with the downward shift of 1 unit, okay, you have again contact with the line y is equal to x. Okay, so this is a case of where you have a vertical shift. Now, if you have, let's say, a horizontal shift, and we have, I say, in this one, I say, we'll take another vertical shift. Let's see if I can. Okay, so just a little bit of a change up. Okay, now, again, this is what we had before with y is equal to 3 to the x. And, okay, notice before I had the subtraction of 1, and so the range, we had the values of y greater than -1. And let's say if I have this time, if I have 3 to the x plus 5, guess what? But what we're going to have in the case of the range with the plus 5, your range is going to be the set of values y, which will now be greater than 5. Think of it like, okay, smallest possible positive number plus 5 is going to be slightly greater than 5. So we have for the range of f of x, we have y is greater than 5, and again, we still have the domain to be the set of all real values in x. Now, looking at what we have in terms of how the inverse is going to arise, as well as what the characteristics are going to be. Okay, so we have y is equal to 3 to the x plus 5. And looking for the inverse. So if I interchange x and y, so we have x is equal to 3 to the y plus 5. Again, so I have that exponential term, 3 to the y. And I'm going to get this expression by itself. So if I take 5 away from both sides, Okay, so we have x minus 5 is equal to 3 to the y. And again, just taking care of 3. Okay, if I apply the base 3 logarithm to both sides, so you have the base 3 logarithm of the quantity of x minus 5 is equal to the base 3 logarithm of 3 to the y. Okay, so we're going to have the base 3 logarithm of x minus 5, okay, is equal to y. And if I switch the order, okay, and so we're going to have just informally stating, okay, so you're going to have the inverse of f of x, so equal to the base 3 logarithm of the quantity of x minus 5. And for this inverse function, okay, so the domain of the inverse, okay, we're concerning what we're going to have in x, and what we're going to have in x, okay, will be what was described for y in the original function. So we have for x, you're looking at values of x greater than 5. And as for the range of this inverse, okay, so it pertains to y in the same manner of what we were pertaining to x for the exponential function. So for y, we're going to have the set of all real numbers. And so for what we're going to have here is that for this exponential function and the inverse that corresponds, okay, so again we have y is equal to 3 to the x plus 5. Okay, so I have this particular curve, and for x at 0, okay, think like 3 to 0 is 1 plus 5 is 6. And I got 1, 8, 2, 14. And like 3 cubed is 27. 27 plus 5 is 32. And if I take the base 3 logarithm of x minus 5, guess what? I got 6, 0, 8, 1, 14, 2, and 32, 3. And notice we have interchange of values for what we had to exist for x and y throughout. Okay, and again, those curves will have symmetry with respect to the line y is equal to x. All right, so those are just some of the visual applications we have regarding the nature of how exponential functions will behave with respect to their inverses, or namely their corresponding logarithmic expressions. All right, now again, yesterday we looked at, or the other day we looked at the natural logarithmic exponential base e, and we had crossover briefly into business applications, and where we have compounding of interest involved, and we have for page 378. Yes, I have on page 378. Okay, and again, we're looking at a situation, okay, where we have $8,000 is financed, and for number 46, okay, so we got concerning the future value formula where we have interest to be compounded. Okay, so you have A is equal to P times, okay, the quantity of 1 plus R over N. We have raised to the N times T power. Okay, and for the values concerned. Okay, so for what is financed, okay, you have P to be in the amount of $8,000. And we have also in the mix, we have the rate of interest, which we have at 3.5%. And again, we're going to express as a non-percent decimal. Okay, so that's going to be 0.035. And for the time span, we're looking at 20 years. So you're looking at the future value of $8,000 after 20 years. If during this time span we have interest to be compounded in the various frequencies at 3.5%. And if I'm looking at annual compounding, okay, so if I have it done annually, okay, so we have, again, this is where the end value is equal to 1. Okay, so we got this formula. Okay, so we have N is equal to 1. Again, P we have at $8,000. So we have R, again we have at 0.035. We have over 1. And again we have 1 times 20. Okay, so I have $8,000. Now we have for the sum, again, that's going to be 1.035. And this will be taken to the 20th power. Okay, now for 1.035 to the 20th, okay, you have like your x to the y or y to the x, or it could be that arrowhead or caret symbol that you will use. And for 1.035 to the 20th, okay, that number is slightly under 2. So you have right at 1.9897. If you keep the decimal places, then we have for that future value, okay, this will be around 15,918.31. So this is the future value whenever compounding is done on an annual basis. Now let's say that just kind of moving up to the next frequency. Okay, so if I'm looking at quarterly compounding, again, we have the same formula, but a different frequency. Okay. And so for here, instead of N at 1, okay, now we have at 4. Okay. Okay, so 0.035 over 4 added to 1. And for this number, okay, we have 1.00875. And guess what? We have 4 times t, where t is at 20, and 4 times 20 becomes 80. Notice some things here. The sum has gotten smaller, while the power has gotten substantially larger. And for this decimal to the 80th power, okay, that one is going to be slightly over 2. So you have among the first digits, and what I had here was 2.0076. And it's keeping what we have here and multiplying by $8,000. So you have about $16,061.05. And if we go out to monthly compounding, again, it's the same formula, but where n has changed. Okay, this time we went from annual at 1 to quarterly at 4. Now with monthly, with n at 12. So the sum is still going to be getting smaller as the power gets larger. Okay, so we're going to have here, so you got 1 plus 0.035 over 12. And this number here, okay, so we got, and it's going to be a floating decimal. Okay, so you have like 1.0029166, and we have just like 6's to repeat throughout. And if you keep this sum and raise to the 240th power, okay, this time around we're going to have still just over 2, and this time we'll have 2.0117. And if you keep the decimal, multiply by $8,000. Okay, so this is going to be about $16,093.62. And then sort of maxing out with daily compounding with the use of this formula. And this time we have with n at 365. Okay, so we've got some changes here. So again, n changes to 365. And for the power, we have 365 times 20. Okay, so basically with 0.035, a small decimal number to begin with, divided by 365, and then we have tacked on to 1. So basically it's almost like adding virtually lent to 1. And for this particular sum, yeah, so just, if I had to give a decimal display, you have like 1.0000, and you have like 958, and whatever decimal numbers come thereafter, and we have this time 365 times 20. So this will be at 7,300. Okay, so this decimal number, okay, to the 7,300th, okay, this is going to end up also a little bit over 2, so you have about a 2.0136 among the first decimals, and multiplying by $8,000. Okay, so we have for this balance, okay, we have right at 16,109.48. Okay, so directly using this formula, okay, daily is going to be the maximum. Okay, but anything beyond this, okay, we have with the continuous compounding. Okay, so with the value of n, now the author has it as not applicable. But if there were any other way of putting this, this is just going to be infinity. And what was this particular statement? Again, as n approaches infinity, this 1 plus r over n to the nt power, that's going to translate to e raised to the r times t. And again, e is that natural logarithmic exponential base number. Again, we have p is going to be at $8,000. And for e to the rt, okay, so r, again, we have a 0.035. And the time span we have for 20 years. Okay, so you have $8,000, and you have times E, and you're going to multiply together R and T. And the product of 0.035 and 20, okay, that's going to be 0.7 or 0.70. And so for e to the 0.7, okay, that's going to be like 2.01375. And just multiplying by $8,000 and putting in terms of dollars and cents. And so in this case, right, so we want to have maxing out to right at 16,110.02. Okay. All right, so for what we started out with, okay, so we have with the annual compounding starting out with $8,000. Okay, so we had that result. We have 15, 9, 18, 31. And then going from 1 time a year to 4 times a year. And we have after 20 years, okay, the quarterly compounding yields a higher balance at 16,061.05. And then monthly. And notice we have for all situations, the percentage rate is quoted at 3.5%, but the more frequently the compounding is done, the more interest is going to be added. So here I have like yet like another $32 plus added as I went from quarterly to monthly, and then going from monthly to daily. Okay, so that's like almost another $16 added still. And daily is almost the max, but just if you notice for the difference, okay, you have just like 54 cents difference as you go from daily to continuously. So as you get closer to the continuous, it's like you're maxing out for the most part, and as you get closer and closer and closer to infinity, it's like going from daily to non-stop. It's like the amount of change percentage wise is virtually negligible. All right, so this is what we have as one case in looking at the compounding of interest, okay, from annually all the way out to what we have with continuous compounding. Now, looking at an application, and we have in the case of number 48, okay, we're looking at the determination of, once again, future value, and we're looking at continuous compounding. And we have starting out with the same principle, the same time span, but where we have change-ups for the interest rates. And just looking at what we have for 48, we're looking at continuous compounding. Okay, so again we have p times e to the r times t. And what is financed? Okay, we have p is going to be at $6,000. And the time span, okay, we're going to have for 12 years. Okay, and you're looking at determining, okay, what is A going to be? What is the future value? And so for what we have in the case of Part A, now you're looking at the compounding of interest to be at 1%. Okay, so you have a 1% interest. Okay, so for your R value, okay, so R is at 1%, and again, I'm going to convert this to a non-percent decimal. So R is going to be at 0.01. So for the future value, you have P times E to the R times T. Once again, P is at $6,000. And we have for E to the RT, so again we have R. We have a 0.01. And T we're going to have at 12. And again, the variable E, this might appear as a second function, and it might appear as e to the x, but it's going to be right around where you have the ln and the lg buttons for many calculator models. And so we have for r times t, so we're looking at e to the 0.12 and for e to the 0.12, okay, that number we have right at 1.1274 and some decimal places after this, and taking e to the 0.12 and multiplying by $6,000. Okay, so you have for that balance, okay, you have about 6,764.98. Now for what we have in the case of Part B, okay, so if I up the interest rate to 2%, okay, so we have for R is going to be at 2%. And to be able to calculate using R, so I'm going to convert R to a non-percent decimal. Okay, so that's going to be 0.02. And just taking what we have now for the future value, and I'm still looking at continuous compounding. Again, starting out with $6,000. You got E, and to the R times T, so I have E to the 0.02 times 12. So we got $6,000 times E to the 0.24. And your calculator might be able to multiply these directly into the final answer, but if you have here wrong number. Okay, so for e to the 0.24, okay, this would be about 1.27124. Okay, so in taking the product, okay, so this would be about 7,627.49. Okay. All right. Okay, so notice, okay, have higher percentage rate. Okay, so the higher the balance. And then we have in the case of Part C, so you have for 4.5% interest. Okay, so you have R is equal to 4.5%. And converting to a non-percent decimal number, so that's going to be 0.045. Okay, so just plugging in the numbers. Okay, so you have $6,000 principal for e to the r times t. So you have 0.045 times 12. And for the product of R and T, okay, that's going to be a 0.54. And for the number here, for e to the 0.54, okay, we have a number that's going to be just over 1.7. And just keeping your decimal result and multiplying by $6,000. And it's going to follow that for the balance or the amount after 12 years. The $6,000 is going to grow to around $10,296.04. Okay, now for the next item, okay, and this is this kind of stresses context whenever we're talking about interest. And now for number 49, okay, you have a deal, okay, where you have $10,000 is financed, okay, and the first option is where you have 5.5% simple interest applied for 4 years. And the other option is where you have compounding of interest, okay, at 5.5%, and you have compounding of interest for 4 years. And the amount financed, okay, we have at $10,000. And it's asking, okay, which option is going to be less costly? In other words, which will result in less interest being applied. And we have for number 49. Okay, now simple interest, compound interest. We're still talking about interest. We're still talking money. Okay, but in terms of percentage rates and all that, how they grow and all that, and the underpinnings and all that, there are some differences. And now we have with the simple interest option. And we have with the simple interest. Okay, so we got, okay, so you have the principal, or what is finance. Okay, we have at $10,000. And for the percentage rate, okay, we have at 5.5%. Again, I'm looking at a non-percent decimal. Okay, so that's going to be 0.055. And we're looking at the time span here to be 4 years. Okay, now with the simple interest, okay, you have simple interest. We're just looking at the formula. I is equal to PRT in other words, how much is going to be added to the $10,000? Okay, so for I is equal to PRT, okay, so you have $10,000 and R, okay, again, we have a 0.055. And the time span is going to be for 4 years. So if I multiply P, R, and T as they are laid out, okay, it turns out that the amount of interest is going to be exactly $2,200. Okay, so that's 5.5% simple interest for 4 years. The only thing here is just I is equal to PRT, and you don't even apply the compound interest formula. Now, for the other deal, okay, now we have at 5% interest compounded continuously. Now for this arrangement, now we're still looking at financing $10,000. Now the quoted percentage rate, okay, we have at 5%. So R we have at 0.05. And the time span, okay, we have for 4 years. Now if you had simple interest involved, of course, you're going to have less interest accumulated since 5% is a lower number than 5.5%. But just stressing what we have with the continuous part for continuous compounding. This is quite a different context from just the simple interest. And so for the continuous compounding, again, we have A is equal to P times E to the R times T. Again, we have $10,000. Then we've got times E, and we have to the R times T, so we have R at 0.05, and T is at 4. Now for the future value, again we have $10,000 times E to the 0.2 and for E to the 0.2, okay, that number we have right at 1.2214. Now the future amount, in other words, the $10,000 is going to grow to around $12,214.03. Okay, remember in the simple interest, that $2,200 is the amount of interest added. Now, in the case of interest, okay, the amount of interest added is going to be the difference between the future value and what was financed. So we're looking at the future value minus what was financed. So we have $12,214.03 minus $10,000. So the amount of interest with this deal is going to be $2,214.03. $214.03. So looking at the arrangements here, now the simple interest, the amount of interest, okay, was at $2,200. So if somebody borrowed with this deal, it's like after the 4 years, that person would owe $12,200. Whereas in the case of the other situation, that person would owe $12,214.03, which is going to be $1,403 more than the simple interest deal. And so in terms of comparing the numbers, we got 2,200 lined up against 2214.03. Okay, so in this case, the simple interest option is going to be right at $14.03. It's $14.03 less. I'll just stress this, okay, now that it's a bit counterintuitive in a sense, because you got the simple interest option at 5.5% with the deal laid out. It's $14.03 less than the continuous compounding at 5% plan. Okay, so the simple interest option at 5.5% is $14.03 less than the continuous compounding at 5% with the very same money to start out with. Okay, and now, so whenever one talks about interest, okay, again, it could be either in the context of simple interest, or it could be we have the compounding of interest. It could be annually, monthly, daily, or in this case, continuous compounding. All right, and now looking at what we have, going back to logarithms. Okay, and again, a logarithm is going to be the inverse of an exponential function. And just some of the properties that we have here. And for among the first items, okay, some of these you can either do quickly by hand, or in some cases you can also use the calculator. And for what we have in the case of properties of logarithms, this is like whenever we're working with logarithmic terms and even logarithms in the case of equations. And one key property of logarithms, okay, and we kind of dealt with this when we went from an exponential function to its inverse. And this is going to be where we have before the base A logarithm. We work with a to the y, but it doesn't matter what variable you're dealing with. Now, the base A logarithm of a to the x. So if you have a match between the exponential and the logarithmic bases, and the exponential bases raised to a power, we're going to have, if there's a match, then this term is going to reduce to the exponent. So you have the base A logarithm of a to the x is equal to x. And just kind of cite some examples here, and just kind of going back to what we had with, say, the calculator terminology. if you have something like log of 100, okay, now unless it says otherwise, whenever you see log, like in the case of a calculator, log is going to be in reference to a base 10 logarithm. So you're looking at the base 10 logarithm of 100. And guess what? 100, it is a multiple of 10, and it is also a power of 10. So in terms of base 10, now 100 is going to be 10 raised to the second. So if you notice in this layout, okay, the value a is going to be at 10, whereas x is going to be at 2. So the base 10 logarithm of 10 to the second, okay, that reduces to 2. Also, with our other feature in many a scientific calculator, if I have something like ln, again, ln is in reference to a natural logarithm. And let's say if I have something like the natural logarithm of e to the negative 4. Now, log by itself translates to a base 10 logarithm, whereas in the case of ln, this is a base e logarithm. So the natural logarithm of e to the negative 4, you're looking at a base e logarithm of e to the negative 4. So here x is at negative 4, and the a is going to be at e. And again, we have an identity between the exponential and the logarithmic basis, so this is going to reduce to negative 4. And if we have something like the base 5 logarithm of 125. Now, in many a calculator, you're not typically going to have anything outside natural or base 10 logarithms. But now, for this statement, I can reduce this one because looking at the logarithmic base, okay, which is 5, 125 is a multiple of 5. And not only is it a multiple of 5, it is also going to be an exponential power of 5, because 125 is going to be 5 raised to the third. And guess what? The base 5 logarithm of 125 is going to be the base 5 logarithm of 5 to the third. And so that is going to go to 3. All right. Okay, so this is one initial property of logarithms, and something that is akin to this. And this is going to be where we have a to the base a logarithm of x is equal to x. Different layout, but you have the exponential base at a, logarithmic base is still going to be at a, and this time we have x resulting from the attachment in the logarithmic base, whereas before we had it as the power to which the exponential base is raised. But we still have in both capacities the reduction all the way down to x. And just give some examples here. Okay, so if I have something like 2 to the base 2 logarithm of 5, guess what? You already have the same a with 2. So 2 to the base 2 logarithm of 5 is equal to 5. And let's say if I have something like 10 raised, okay, to the log of 2. So here, log, okay, it's going to be in reference to a base 10 logarithm. And here we're going to have 10 to the base 10 logarithm of 2. Guess what? Your a is going to be at 10, your x is going to be at 2. So this is going to reduce to 2. And if I have something like e to the natural logarithm of 12, so e to the ln of 12. Again, you got your exponential base at e. Now natural logarithm again is going to be a logarithm in the base e. So you're looking at e to the base c logarithm of 12. So if you notice a is at e, and your x is going to be the result in this case, which is going to be at 12. Okay, so you have these formulas. Okay, you have close relatives of each other. Now, again, your calculator has natural and base 10 logarithms. And if you have situations where you're trying to approximate a value that is in a logarithmic base other than 10 or e, you will have what's regarded as a change of base formula. Okay. And for the change of base formula, now what this is going to be is that if you have something like base a logarithm of m, what you're going to do here is that for the base a logarithm of m, okay, if the base a is not present, say, in a calculator, you can write this in terms of a logarithmic base that is present. So what I'm going to do here is that I have the base a logarithm of m, we can say is equal to the base b logarithm of the attachment m all over the base b logarithm of what was the original logarithmic base. And what I mean by this is that if you're converting, the base b logarithm could be either natural logarithm, like the natural logarithm of m over the natural logarithm of a, or it could also be the base b logarithm. You have your choice. It will come out to the same reduction. It could also be log, like base 10 logarithm of m all over the base 10 logarithm of a. And just examples here. If I've got, let's say, the base 3 logarithm of 17. Okay, so I have like the base 3 logarithm of 17. Okay, now, chances are you're not going to have a base 3 logarithm, but you can still use ln or log to determine about what this number is going to translate out to. Okay, so in this particular case, we'll take the natural logarithm. So here we have a is at 3, m is at 17. If I go with natural logarithm of m, this will be natural logarithm of 17, and you have divided by the natural logarithm of 3. And let me mention, if you're taking this ratio, you had to put in the natural logarithm twice. You got natural logarithm of 17 divided by, and you had to re-enter natural logarithm of 3. You cannot do it as natural logarithm of 17 thirds. That's going to get you an entirely different number. And okay, so just in terms of how it might appear in your calculator, so you have like ln 17, you have /, you can have ln of 3, and for the display this is going to be around 2.579. And let's say if I were to use, let's say a base 10, if I use the base 10 logarithm here, log 17 over log of 3, I'm still going to come out to the same value. And let's say that if I go with something where we have a is going to be a decimal number, and we'll say that we have, the logarithmic base to be at 1/2. So I'm looking at the 1/2 base logarithm, or the base 1/2 logarithm of 20. Okay, and if I go with log, let's say, it'll still work with ln. So here your m is represented by 20. And a is represented by 1/2. Okay, just for the notation, okay, so we have log of 20 all over log of 0.5, and for this output, okay, this is going to be a negative number, and say to about the nearest 3 decimal places, this will be about a minus 4.322. Okay, so with these properties, okay, we are dealing with single terms, and now just looking at what we have concerning properties of logarithms, and we're going to have, let's say, just another case here. Okay, if you notice, okay, first two properties, you had a match between the exponential and the logarithmic base. But now, so again, just going to stress this, okay, it's just a little bit of a backdrop. We have the base A logarithm of a to the x is equal to x. But let's say that if I don't have a match, say if I have something like a base A logarithm, and instead of a, we have m instead. So if I have like base A logarithm of m to the r, that could be x as well. Okay, so you have base A logarithm of m to the r. Now that which is in the exponential position, I'm going to rewrite as a coefficient. So we have r times the base A logarithm of m. And in terms of how this might look upon first glance, okay, if I have something like a base 3 logarithm of 5 to the t power, so we have a at 3, m at 5, r at t, and I have to rewrite this with the exponent as a coefficient. So this is going to be t times the base 3 logarithm of 5. And let's say that if I have something like another term, if I have the base 2 logarithm and I have of the quantity of x plus 4 raised to the third. Okay, so notice you have a is represented by 2, m is represented by the binomial x plus 4, and we have r is going to be represented by 3. Okay, and so just reworking what we have here. Okay, so a is at 2, m is with the binomial x plus 4, and r is represented by 3. And so just rewriting the exponent 3 as numerical coefficients. So we have 3 times the base 2 logarithm of the quantity of x plus 4. And let me stress this remaining part here. If I have, let's say, I had a binomial as an exponential base. Let's say if I have it as an exponent, and say if I have base 5 logarithm of t raised to the y plus 4. Okay, now the inclination might be to write this result out. Okay, so you have a is at 5, m is at t, r is at y plus 4. And the initial impulse might be to write this as y plus 4 times the base 5 logarithm of t. Okay, so that is partially correct, but to make it entirely correct, if you notice, without parentheses, y looks as if it might be detached from the rest of the terms. So that might be read as y by itself, and then you got plus 4 times the base 5 logarithm of t. But still, I'm going to have all of y plus 4 to be multiplying the base 5 logarithm of t. So I'm going to need parentheses. And just So you need the parentheses in this particular conversion. And now let me kind of leave you with this. And this is where we're going to kind of transition away from just standalone terms into logarithms. Now for the sums and differences of logarithms. Okay, there'll be two key formulas. And I'll show you the converses as well. Okay, you're going to have like a base A logarithm of m times n, and multiplication in the attachment is going to translate out to the operation of addition between logarithmic terms where the factors are a bit detached. So the base A logarithm of m times n is going to become the base A logarithm of m plus the base A logarithm of n. And again, the converse is going to ring true, where we had the sum of separate logarithmic terms in the same base, where addition is going to translate to multiplication of the attachments. So you're looking at the base A logarithm of m times n. And if we had the operation of division, say we had m divided by n, division here is going to translate to subtracting. So we're going to have the base A logarithm of m minus the base A logarithm of n, and it also works in reverse fashion. Okay, so division translates to subtraction, and it also works in the reverse whenever you are combining logarithmic terms and making as a single expression. I know it's quite a bit of material to cover today, but I'm trying to give us some breathing room because, believe it or not, we have like less than 3 weeks to go before wrapping up this semester.